Every time you open an application, launch a video game, or browse the internet, your computer needs to temporarily store a massive amount of information. This task is handled by a discrete, yet essential component, random access memory, better known as RAM. Without RAM, a modern computer would be unable to function efficiently. It acts as an ultra-fast workspace where the processor can instantly access the data it needs. The faster the RAM and the more information it can temporarily store, the more complex tasks your computer can perform. But behind the simple memory module installed on a motherboard lies one of the most sophisticated manufacturing processes ever developed by humanity. It all begins with an unexpectedly ordinary raw material: sand. Sand contains silica, a chemical compound made primarily of silicon and oxygen. However, the silicon used in electronic components cannot be extracted directly from sand and immediately turned into computer chips. It must first undergo a long series of transformations designed to remove nearly every impurity. Manufacturers produce ultra-pure silicon that can reach purity levels above 99.9999999%. At this scale, even the smallest contamination could render thousands of future chips unusable. Once purified, the silicon is heated to extremely high temperatures until it becomes liquid. Engineers then use a process known as crystal growth to create a massive single crystal. Unlike ordinary materials made of multiple randomly oriented crystals, this crystal possesses a perfectly uniform atomic structure. This enormous cylinder of silicon, known as a silicon ingot or boule, can measure several dozen centimeters in diameter and weigh hundreds of kilograms. The ingot is then sliced into thin discs called wafers. These silicon wafers form the foundation of all future electronic chips. At first glance, a wafer looks like nothing more than a shiny metallic disc, yet it will soon contain billions of microscopic components. The manufacturing process begins inside one of the most controlled environments on Earth: the clean room. Inside these facilities, the air is continuously filtered to eliminate dust particles. A particle invisible to the human eye can be larger than some of the structures etched onto modern chips. This is why technicians wear full-body protective suits that completely cover them from head to toe. The wafer is then coated with a light-sensitive material called photoresist. This layer reacts to light and allows engineers to draw the future electronic circuits. This is where the most critical stage of semiconductor manufacturing begins. Extremely advanced machines project microscopic patterns onto the wafer using ultraviolet light. These patterns serve as construction blueprints for the future electronic components. After exposure, specific areas of the photoresist become soluble and are removed during development. The design of the circuit gradually appears on the wafer's surface, but this process does not happen just once. It is repeated dozens, sometimes hundreds of times. Each cycle adds a new layer or creates a new structure within the chip. Between lithography steps, manufacturers use chemical and plasma etching techniques to precisely remove selected materials. Other machines do the opposite, depositing new atomic layers of silicon, insulating materials, and metals. Little by little, an incredibly complex architecture is built inside the chip. The goal is to create the memory cells that will ultimately store information. In modern DRAM memory, each cell consists of just two primary components: a transistor and a capacitor. That may sound simple, yet a single memory chip contains billions of these cells. The capacitor acts as a tiny electrical reservoir capable of storing a charge. When the charge is present, cell represents one binary state. When the charge disappears, it represents the other. The transistor acts as a switch that allows data to be written. All of these cells are organized into an enormous grid. Billions of bits can therefore be stored on a surface smaller than a postage stamp. As the cells are being fabricated, engineers also build the metallic networks that allow electrical signals to travel throughout the chip. These connections are created using copper and other conductive materials, deposited with nanometer-scale precision. When all the layers are completed, the wafer now contains hundreds of identical memory chips. However, not all of them will function correctly. Manufacturers perform an initial series of inspections directly on the wafer. Automated testing equipment evaluates each chip individually to identify defects. Faulty chips are marked, while the best-performing ones continue through the manufacturing process. The wafer is then cut using extremely precise saws. Each small square produced becomes an individual memory chip. These chips are then packaged inside protective housings. Packaging serves several critical functions. It protects the internal circuitry from moisture, mechanical damage, and environmental contamination. Inside the package, microscopic connections link the chip to its external contacts. Some are created using ultra-thin metallic wires, while others rely on more advanced technologies, such as flip chip packaging. Once packaged, the chips undergo another extensive series of tests. Manufacturers verify their electrical stability, power consumption, operating speed, and resistance to temperature variations. Some chips are capable of operating at higher frequencies than others. These are sorted into different performance categories. The manufacturing process then moves on to the RAM module itself. The foundation of the memory module is a printed circuit board specifically designed to host multiple memory chips. These circuit boards are manufactured in automated facilities where layers of copper are etched to create the required electrical pathways. The memory chips are then automatically placed onto the circuit board by ultra-fast pick-and-place machines. Some of these machines can position tens of thousands of components every hour with remarkable precision. The components are permanently attached using a process known as reflow soldering. The board passes through an industrial oven where solder paste briefly melts before solidifying, creating permanent electrical connections. Depending on the model, additional components may also be installed. Modern DDR5 memory modules, for example, include dedicated power management circuits directly on the module itself. Some modules also receive heat spreaders designed to improve cooling performance. Once assembled, the memory modules undergo a long series of validation procedures. They are tested under different temperatures, workloads, and operating conditions, sometimes running continuously for hours. Manufacturers search for even the smallest defect that could appear after years of use. Only modules that meet every specification are approved to leave the factory. They are then packaged, shipped to logistics centers, and distributed to computer manufacturers and retailers around the world. A few weeks later, they find their place inside a laptop, workstation, server, or gaming computer. At that moment, billions of transistors and capacitors, manufactured with nearly unimaginable precision, begin working together. Every click, every image displayed on a screen, every document opened, and every game launched depends on their operation. Behind a simple RAM module lies decades of scientific research, some of the most advanced factories on Earth, and manufacturing processes capable of manipulating matter at the nanometer scale. A small and often overlooked component, yet one that remains absolutely essential to modern computing.